Saxon Algebra 1, Lesson 82. Today we are not going to learn any new math concepts. We're going to learn a couple new vocabulary words. You already understand how these words work. We're just putting a name to them. Domain is the fancy name for values when I show you the problem, you'll know exactly what I mean. Domain means the values that we plug into an equation. Usually, we associate them with the letter X. Range is the solution that we get when we solve the equation. We typically associate this with the letter Y. Function is the name for the function is the equation that connects the domain to the range, okay? So we have a function, we plug in values for the domain, and we calculate the answers, which we call the range. Let's look at some problems so that you can see what we're talking about. The sun's going down, but I think there's still enough light. Now I'm going to change this problem ever so slightly. So that it looks familiar. Okay, we've done many problems like this, right? We're supposed to take this equation and plug the 5 in everywhere there's an X and then solve it. This is what we call the domain. This is what we call the function. There's a little bit of decorations we're going to add to this, the way we write it in just a minute. But we're given the function, and we're given the domain, and we're told to find the range. Okay? This is what we use for X. This is what we plug it into, and we're asked to find the answer. So what we do is we take this, right, this function, and we enter the domain, and then we solve it, right? That would be 25 plus 5 minus 10. This much is 30. 30 minus 10 is 20. Okay, so that is a lovely answer. Now, what I'm going to do is add just a few little flourishes in the way that I present this information. Instead of writing this separately, I'm going to write the f of x, the function. This is a title that means function. The name of the function is f. Right? We said this was the function, so now I'm just putting a little fancy symbol in front of it to say, oh, this is the function f. We're calling it f. You'll see there are other letters we use sometimes, but right now I'm just using f. And it's this same equation, right? That's the function. Function equals equation. But now, instead of saying let x equal 5, we say find the f of 5. What that means is exactly what this means. Take 5 and plug it in for every x. So we say the f of 5 equals 5 squared plus 5 minus 10, which equals 25 plus 5 minus 10. So we would say that the f of 5 equals 20. Same exact answer. The calculation's exactly the same. All that we're changing are the words we use and a few little flourishes in the way we write it down. The function of x, the f of x equals this. Find the f of 5. That just means plug 5 in everywhere there's an x and solve it. The math is exactly the same. This is called function notation. Notation just means how you write it down. And there is no change in the math. It's just stylistic issues. The reason I'm stressing that there's nothing new here is because these words often confuse students and make them feel like it's something completely different and new. And it's not. And the reason that's important is because when you advance to college level math instructors love to talk with function language. They love to talk about domains and ranges and functions. And so it's important to me that you see that you already understand what it means. You just need to get used to hearing those words. So I'm going to toss them about. Even John doesn't toss them about a lot. I'm going to toss about them more than John does in the future. But right now, we're just going to run through a few more problems. I think I need lights though. Let's see if that is enough light to get us through. I think so. I've created some nasty shadows, but we'll see what we can do. 82.2. There are quite a few examples in this. Oh, let me get my light. Hang on. Okay, I'm back. It's kind of a low-tech production, isn't it? Okay, now we can see what we're doing. That's very helpful. What with the whole writing, right? Okay. Oh, that's nice and bright with a little glare in the screen. Why not, right? Okay, let's do example 82.2. If the h of x, okay, so this function is named h. The h of x equals x squared plus x plus 1. Okay, that doesn't scare us. That's the function. This is the name of the function. This is the actual function. Find the h of a squared. Okay, so this is our domain for this problem. We take a squared and we plug it in to this, okay? We remember to just think in terms of buckets. So this is a squared squared plus a squared. I don't really need these buckets, but sometimes it's just helpful to use them. Plus 1. Okay, I took the domain that they requested, John requested, and we plugged it into the h function. This is the name of the function. There it is. And we get that the h of a squared equals, ooh, look, that would be a to the 4th plus a squared plus 1. And that's as far as we can take it. We can't simplify that anymore. Okay? This is the range of this function. And one of the things about functions that people like to stress over and over is that there is a mapping, there is a connection between the domain and the range. Every single time I plug a squared into this function, I will always get this output, this answer, this range. I'll always get the same answer here. So that sounds like a big fat nothing burger, but it's a really big deal when you get into higher mathematics. Functions are dependable, they're consistent. Every time you plug the same thing in, you'll get the same answer. Yay, life is simple. And you're probably right now thinking, well, of course you always get the same answer. Like, that's not even something to think about, but yeah, it is. Okay, if the f of x equals x squared plus 1. Okay, this is our function. This is the name of it. This is just the way we write. Here's a function. It looks like this, and now we're supposed to find the f of x plus 2. Oh, what that means is that everywhere there is an x, we're now going to put an x plus 2, and buckets are the way to go. X plus 2 squared. Ooh, see how this goes in the bucket? Then we have to square it, plus 1. All right, well, we can do that, right? Let's go ahead and do our dance. Remember how we multiply binomials? We'll do x plus 2 times x plus 2. These are the boys and the girls dancing in the studio, right? On Saturday morning. The boys are in this row, the girls are in this row. This girl dances first. Dancing is actually multiplication. X squared plus 2x. Now this girl has danced with both boys. She sits down. This girl gets to dance. Here's another 2x, so I'll line them up together. And then plus 4. So when we multiply out this binomial, we get x squared plus 4x plus 4. So now I'm going to write that in here. X squared plus 4x plus 4 plus 1. So our final answer is that the f of x plus 2 equals x squared plus 4x plus 5. And that is our final answer. And again, what we're saying is that we're taking the value of x plus 2 and we're plugging it into this function named f, and that's what we get out, right? Domain, range, and this is the function, right? The original expression. Well, this is the function given our domain, right? I'm going to stop talking now because I'm making it harder than it needs to be. All right? So the calculation you see is nothing but these problems we've been doing forever. Okay. Now, sometimes we can talk about domain and range instead of as specific values like we were there. If you plug in 2, you'll always get 20 or whatever. We can talk about domain and range in a broader context, and that's what we're going to do in these next couple problems. Okay. I'm going to write it down just so we can look at it. Okay, so here's what we're looking at here. This is our function. We named it function f, and it's a very simple little function. It says just simply take the input, the domain, and multiply it by 2. And that will give you the answer or the range. Now, what we're asking ourselves in this question is, are there any limits of any numbers that we can put on this? Is there any reason why we would run into problems with different values for x? And we say, no, you can multiply anything by 2, right? And you'll get anything times 2 out as your answer. So in this one, what we say, and it's so easy and simple, it's almost confusing. We say it's fine to plug any real number into this, and as the result, when we plug any real number in, we'll get any real number out. It's obvious. It's easier if John would have started with a more limited situation, but he didn't. So what we say is that the domain of F equals the set of all real numbers, right? Remember our chart where we talked about counting numbers, whole numbers, integers, rational numbers, irrationals over to the side, and then real numbers, meaning all of that. What we're saying is when you're picking out values to plug into this function, you can choose any of them. You can choose fractions, decimals, you can choose pi if you want. It doesn't matter, you can plug anything in there. And what you'll get out in the range, the output, you will also get all kinds of real numbers. There'll be 2 times whatever you put in, but you can get any real numbers, it'll be fine, right? That's the way we write the answer to this problem. I know, that's so easy and weird, it almost sounds confusing. This will make a lot more sense when John gives us some examples where we can't put anything in. And you know what, I'm gonna make up a problem because John doesn't have a good one here. What if we said the f of x equals 6 divided by x? Okay, are there any limits? So we're gonna find the domain and the range of this function, right? Now, what we know is that we can put a lot of numbers down here, right? We can put fractions or decimals, we can put big numbers, small numbers, but there is one number that can't go down here. X cannot be equal to 0. Because if this is 0, it will blow up the kingdom, right? And the kingdom and the universe, right? So we cannot let this be 0. So we would say that the domain is the set of all real numbers except 0. Do you see how that would change it? Because we can't allow anyone to plug 0 in there. Once we fix that, then the range will be all real numbers again. We can get anything out. We've already said no zeros involved. So we would say, there's a fancy way to say it, but I just want you to see that that's an example where we would have to restrict the domain because we cannot allow 0 to show up in that denominator. Oh, is that the next problem? Oh, I knew it. Example, let me just jump down to it. 82.8. Find the domain of the function g of x equals 1 over x. And there is exactly what I'm talking about. I thought I was making it up. Now let me show you the fancy way to write it. We would say the domain of g, the numbers that you can plug into function g, equals the set where x is an element of the real numbers, meaning x can be any real number such that, this line means such that, which means, here comes some details, x cannot be equal to 0. This is the fancy way of writing this. All right, this is saying we can't, our domain has to be limited so x can't equal 0. And here is a fancy way of saying that very same thing. You will eventually memorize this kind of presentation. For now, it's perfectly fine to look at your notes to remember all of these gibberishy symbols, but eventually you will remember that. Okay, this was my example, but it ended up being exactly like 82.8. Okay, let's go back and fill in some of these others. 82.5 is kind of interesting. It says if the f of x equals 5, find the domain and range. Okay, this is so weirdly simple, it hardly even seems like a function. What this is saying is that you can plug in any number you want to this function, and you're just going to get 5 back out. So the domain is equal to the set of all real numbers, meaning we can plug in anything we want. I mean, that just seems kind of weird because there's nowhere to plug it, right? There's no x's in here, but okay. So we can plug anything in, right? We can say, oh, let's find the f of 2,543. But the truth is that every answer is going to be 5. So the range is 5. That's all you're going to get out of this function ever. Okay? This is a shorter way of writing the domain and range. There are multiple styles, and we're going to experiment with all of them, but all they are is stylistic issues. Now, here comes a kind of domain and range problem that I enjoy. It's a little breath of fresh air. If the graph of function f is as shown, find the domain and range. Okay, so I'm going to draw this little graph that's in your book. Okay, it's got a circle here. Let me fill in some of these numbers. So here, at the point -2, +3, there's an open circle. Then it comes down here, and then it goes up to a dot at 3, 4. Okay, so we're supposed to find the domain. Okay, that seems impossible, doesn't it? But let me show you what the trick is. Remember how I said domain is associated with x? Oh, I don't want to write it like that. I'm just going to put it up above. The domain of this function is the range of values on the x-axis. So see how it goes from -2, but not including -2, because that's a circle, right? And then a hard dot at 3. So what we want to say here, I'm going to say it first a simple way, and then I'll say it the fancier way, that x is between, it's greater than -2. It does not include -2, so I'm not putting an equal sign there. And then it goes all the way up, including 3. Do you see how I've written, it looks like an inequality, but what it really is describing is the high and the low point of the x values. It includes 3. It does not include -2. That's why I chose to write it. Okay? Then we said range is associated with our y values. Remember I said that way back in the beginning? So now what you have to do is readjust your brain and look at this picture now based on the highest and lowest values on the y-axis. We see the lowest value is 0, and that's a solid dot, so we can include it. We're looking at the y's, not the x's. And then the highest value is 4, and again, we include that. Okay, so that is a different way of writing domain and range. We have to make it, this is the simple version. Let me show you the fancy version. It's going to mean the very same thing. It just has more bells and whistles. We would say domain of f equals all the values of x that are an element of the real numbers such that x is between -2 and +3 inclusive. That's a way to say that. It's between -2 and +3 inclusive. By saying inclusive, I mean and -3. Okay, so that looks exactly the same as that. This is all just fancy details. And then for the range of f, we'd say that y are all elements of the real numbers such that they fall between 0 and +4 inclusive. Means we put the equal signs on both of them. Okay, this is the fancy version of the answer. But if you can understand how I got this, then that makes sense. First we look at this in terms of the high and the low point on the x-axis. Then we rearrange our brains and look at the high and the low point on the y-axis. Okay. And let's see, I think, have we done them all? We have the number 7 to do. I did them out of order and that's confusing. 1, 2, 3, 4, 8, 5, 6, okay, 7. Just making it hard on myself, aren't I? Find the domain of the function f of x equals, okay. So what we're saying is, what numbers can we plug into this equation and still have everything be okay? Now, we haven't talked a whole lot about this, but in an even numbered pig house, right? This has an invisible 2 here. We can have positive numbers only. In an even rooted pig house / radical. Okay, what that means is that that number inside there, it can get to 0. I'll better write that, and 0. 0 is okay. We can find the square root of 0, but we cannot allow negative numbers in here. So what that means is that 5 minus x has to be equal then or greater to 0. Does that make sense? Because we can never let this turn into a negative number. So it can be equal to 0 or greater than, but it can never be equal. Then we just solve this inequality by adding x to both sides. And then I'm going to flip it around. And that means that we have to limit our choices of x to be equal to 5 or less than 5. We cannot have numbers greater than 5 in our domain. We can't plug in numbers greater than 5 because that will turn this into a negative and things will go badly wrong. So this is the limitation we want to put on our domain. Now, how do we write that in an all fancy-like style? We say the domain of f, that's just the name of this function. Typically, we start with f's and go g, h, I, j, k. You can go all the way around the alphabet and come back to e. And then if you want to keep going and have more functions, you can do double f, double g. Right? FF, GG. Function notation is really helpful when you have a whole bunch of equations that you're looking at. Maybe not a whole alphabet full, but a lot. Okay, what am I doing? I'm writing this fancy like domain of f. And we were only asked to find the domain in this one. The domain of f is that x can be any element of the real numbers. Sometimes we put that double line R there. That's extra fancy functional notation. Such that x is less than or equal to 5. Okay, that's our official answer. We can plug anything into this function, equation, whatever, equation is what we've always called it. Function is our new name for this thing. Just because this is sitting over here, we know, oh, look, it's a function. This function, we can plug any number into it, fractions, decimals, anything, we can deal with that, as long as this number inside of here never goes below 0. So we figured out that, okay, we can't let x be anything more than 5, or this thing will go into negative numbers. This is how we write that in a fancy style, okay? We'll talk more about functional notation, the style of presenting problems. We'll talk more about domain and range. What I want you to take away from this lesson is that the calculations are not changing one little bit. It's just a stylistic issue. It's like the difference between learning how to print and write in cursive. All the words are still spelled the same way. You're just writing the letters in a slightly different style. That's the best way I can explain function notation. It's like cursive. It's the very same word, it just looks a little fancier. And these are the very same problems, they just look a little fancier. That's all. Lesson 82 is now done. Thank you, goodbye.